Go
Wait,
for
can we
it.
try this next week?
Nope.
Okay, I'm Monet Chandler, and I'll be presenting the 12 principles of green chemistry. So green chemistry is a design used to help like reduce and eliminate the hazardous waste. It's for us humans, really, and animals and everything else. And it first was launched in 1991 by the EPA. So once again, it's a design designated to help eliminate the generation of hazardous waste. And the father of green chemistry is Paul Anastas. So who is he? He's currently the director of Yale University Center of Green Chemistry and Green Engineering. He was appointed by Barack Obama as the agency assistant administrator of research and development. And this is him. He looked kind of scary right there. Like he looked like he's scared of his job. If I had that much responsibility, I'd be scared too. The first principle of green chemistry is prevention. Anastas believes that it is better to prevent waste than to treat it and clean it up once it's started. So that's why we have things like the MSDS that we go by and lab safety and other signals to help us cut back on preventing the waste that we produce. The second principle of green chemistry is synthetics. And he believed that synthetic methods should be designed to maximize the incorporation of all material used. So with this principle, he wants us to go more towards 100% yield instead of having a 50% yield and not using up all the material during our experiment. And here, the peroxy acid and alkaline are used, and it generates 100% yield because everything is being used up in the end. The third principle of green chemistry is human health. And this also ties into the last principle because he wants synthetic methodology to be used and designed in order to make toxicity less for human health and in the environment. And here's an example of that principle. So we have the polycarbonate synthesis up here. And the problem with that is it has a high toxicity and it's corrosive. And it requires a lot of CH2, Cl2. And here we use the solid state process of the polycarbonate, and it eliminates the use of CH2, Cl2 altogether, and it's a higher quality polycarbonate, and use the solid state of it. The fourth principle is reducing toxicity, and as you can see, most of these principles all tie into each other because this is reducing toxicity, and then the last one was reducing toxicity for human health. And so here, the chemicals produced should be designed to preserve efficiency of function when reducing toxicity. And this is dichloro 4,5-dichloro 2N-octyl, blah, blah, blah. Very long name for C9. And C9 is used for marine biology, really. And so this is a cleaner kind of thing that they use on boats where the organisms, once they attach to the boat, the proteins attack them to the point where they would want to leave away and go and find somewhere else safer to live or stay on or whatever. So this is the safer way, and it reduced the toxicity for the marine life. The fifth principle of green chemistry would be auxiliary substances. And the use of auxiliary substances should be made unnecessary whenever possible. So here's a list of preferred solvents that we would want to use. Like whenever you can use these solvents, you would want to use them instead of using this stuff. So you would go down this list first. If you can use anything from there, you would want to use it. And then this list is not preferred, but it's usable. And this, you do not want to use this stuff at all. The sixth principle of green chemistry will be energy. Energy requirements should be recognized for their environmental and economical impacts and should be minimized. So that's why all of us are familiar with this, which is the ice bath. We did that in general chemistry, and you want to use ice baths to cool your substances and solutions instead of using like the refrigerator, which uses more electricity and voltage and stuff like that. And then over here we have the a chemical microwave, and that's also used to heat subsistence and doesn't use as much energy as waiting on a hot plate or something to heat up. The seventh principle of green chemistry will be economically practical, and raw material of feedstock should be renewable rather than depleting, which means like we want to recycle. We want to use our material again if we can't use it. That's why we have stuff like recycling paper or wood or recycling period. We just want to recycle and use stuff as much as possible so it won't go to waste. The eighth principle of green chemistry will be derivatives. And you should avoid unnecessary derivatization and including blocking groups, protection, temporary modifications of physical and chemical processes. And I would like this quote. I found it online, and it was, protecting groups are used because there is no direct way to solve problems without them. We always want to protect a group. Without a protecting group, there's no way to solve them. And stuff here is like an example of carbolic acid, and it just shows how it moves to the derivative of the original, the amide. The ninth principle of green chemistry would be catalytic reagents, and they are superior to stoichiometric reagents. Catalytic offers advantages that reduce reaction times, which is helping minimize energy, which also ties into two principles ago, which was principle 7, sorry. Stoichiometric reagents is the primary cause of generation of waste. Therefore, with the help of catalytic reagents, the amount of waste will be reduced. And here we have the glucose substrate binding into this area right here, the enzyme. And the benefits of using biocatalysts, which is what is being shown, is a faster reaction time, and the orientation of site gives high stoichiometricity, and the waste is soluble. And we also want to use these things because they're biodegradable as well. The 10th principle is degradation, which is really summing it up to biodegradable as well. It should be designed so at the end of their function they do not persist in the environment and break down into degradation products. So we use stuff like corn and wheat and agricultural waste in future. And then, so in this polyic acid, it can be recycled and composited. So we will have 20 to 50% fewer fossil fuels than conventional plastics. And here it's just a cycle of life pretty much. So you have the polylactic acid moving to carbon dioxide, which moves to glucose and then to lactate. And then it goes around, and that's just how it biodegrades into the earth and back out. The 11th principle of green chemistry is analytical methodology, and it needs to be used to develop and allow for real-time and process monitoring and control prior to formation of the hazardous substances. And knowing when the product is done helps to save waste, time, and energy. So we all know when we titrate, we want to see color change. And this ties into this principle because when we see the color change, we know we're at equilibrium and we're done. So doing things like titrations and everything, looking for color changes will help us to know the real time of when to stop our analysis or to stop when we're collecting and everything. The 12th principle of green chemistry is accidental prevention. And we don't want any accidents to happen, of course. As scientists, we want to be safe at all times. So that's what this principle is. We don't want anything accidental to happen. In India, in 1984, there was a poison gas leak at a place called Union Carbide Factory, and it killed thousands instantly, injuring many, and also a lot of people died later after the fact due to exposure. Up to 20,000 people died as a result of exposure instantly. And the methyl isonate, it was used to make pesticides. It was being stored in large quantities, and pretty much water got to it and reacted to it badly. And here are some pictures. Of course, that was a long time ago, so it's black and white. And so if you look at that picture closely, it's like you can see the fumes and the gas and the pollution that it caused. And these are like people laid out dead, and then they're carrying people out pretty much dead as well. And this is the site 32 years after that, and you can still see how corrosive it was, and it was just bad. It actually, if you look up accidental prevention, this is one of the top stories that pop up as far, because it was so big, I guess. But I mean, we weren't thought of then, so I wouldn't even know. So those are 12 principles of green chemistry. Do you have any questions for me?
Yay.
Yay. And then my references are here. Any questions?
Questions?
Monet, when you taking organic chemistry?
Next year, next month.
You're gonna learn how to read all that.
Yeah.
Anybody?
No questions?
Anybody? If you go back to your auxiliary substances. Wah, wah, wah. Did you ever find out whether these were just talking about solvents, since all these are solvents?
Yes, they were solvents, and it was the preferred, not across, but down each row.
Okay. And the preferred are listed there because of their, I suppose, I guess innocuous with respect to if they were dumped into the environment.
Yeah, I guess.
But then the yellow ones are questionable.
Those are the ones that could be used, but we prefer not to use them.
And some of the undesirable ones are kind of obvious, like chloroform or any of these ones that have halogens on it, but I guess I find it strange that pyridine is there, or
That came from
the straight chain.
ACS.
Yeah, right. So I'm kind of wondering why those are all grouped together, since I would think that some of those would be far worse than others, but I don't know. Go forward 1 or 2. Keep going. Whose quote is that?
Oh, I forgot to add that. That was one thing I forgot to add.
Okay. For the derivatives that you have listed, certainly those are derivatives as far as kind of changing the functional group. Nor, I think what this is really talking about with respect to, say, synthetic methodology is really referring to blocking groups, and the idea that when you do specific reactions, if you're working with a complicated molecule, some of the functional groups need to be protected from being converted, depending on what type of reactants are thrown in there. So like p-tosylate and that type of things are kind of normal blocking groups, which is a little bit different than the kind of change in functional group that you've shown here. But since you haven't taken organic yet, you'll figure that out. If you go forward to the degradation cycle, so CO2 gets converted into glucose by plants. What is converting the glucose into lactide? Is this metabolism within the human body? Or where's this cycle coming from? I understand the first point, I understand the last point, the PLA being biodegraded. But how do we go from glucose to lactide and lactide to PLA? I assume lactide to PLA is some kind of an industrial process.
I guess by pooping.
By pooping? What happens by pooping?
You said that's how you get from glucose.
To the lactide? By pooping. Go ahead. And go forward 1 more. 2 more, I guess. What is an exothermic molecule? Methyl isocyanate is a highly reactive.
No, because he told me to change that, but I forgot to take it out.
Yes, yeah. So that's not a thing. So,
Exothermic means it releases energy.
right, which is for a chemical reaction, is not for a molecule. Okie dokie. Thank you, Monet. Who's going next? Michaela, Lucas. You both stand up. 2 enter, 1 leaves. I don't care, whichever.
What would you?
I can
Go
just go
first.
up. Mine is longer.
Well,
Oh, y'all got 15 minutes.
Oops, did it?
well, I'm trying.
Keep it 15. All right.
Hold on.